Welcome to the ABB UPS Sales Training. Level 0. UPS Main Parameters. Training Content. UPS Parameters. Efficiency. Power Rating. Power Factor. Harmonics. Voltage Unbalance. UPS main parameters are: on the input side, input current harmonic distortion, input power factor. Input voltage harmonic distortion is mains dependent. On the output side, output voltage harmonic distortion, output power factor. Output current harmonic distortion is load dependent. If we look at the UPS, we have UPS efficiency, UPS apparent, active and reactive power. UPS efficiency. AC to AC calculation. The total AC-AC efficiency of a UPS is defined as input to output efficiency without charging the batteries and is expressed in %. The total efficiency is split into rectifier efficiency and booster/inverter efficiency. The total AC-AC efficiency is up to 97.4% and is dependent on the UPS type. UPS power. Penalties on electricity bills. Managing an installation with a low power factor implies an increase of costs for the power supply authority, who consequently applies a tariff structure which penalizes the withdrawal of energy with low power factors. The legislative measures in force in the different countries allow the national power supply authorities to create a more or less detailed tariff system structured so that the absorbed reactive energy exceeding that corresponding to a power factor equal to 0.9 must be paid according to defined amounts depending on the voltage level of the supply, low, medium or high, and on the power factor. Reactive power. Reactive power is a quantity defined for AC systems and measured in volt-amperes reactive. Voltage and current in AC networks alternate up and down with the frequency of the supply but not necessarily at the same phase angle. The current phase shift can be described by two components. Active current, in phase with V, reactive current, +/90 degrees shifted. The power transmitted also alternates and goes up and down but with twice the frequency around some average value. This average value is called real power. Active and reactive power differences. Active current, current active component. In phase with the supply voltage directly related to the output. Represents the part of electric energy converted into energy of different types, mechanical energy, light energy, thermal energy. Reactive current, current reactive component. Perpendicular to the voltage. Used to generate the flow necessary for the conversion of powers through the electric or magnetic field represents an index of the transfer of energy between supply and load. Power triangle. Since real and reactive currents are 90 degrees shifted to each other, we have a triangle relationship. The same relationship is known from the power triangle. Harmonics introduction. Harmonic currents are created by nonlinear loads connected to the power distribution system. Harmonic distortion is a form of pollution in the electric plant that can cause problems if the voltage distribution caused by harmonic currents increases above certain limits. All power electronic converters used in different types of electronic systems can increase harmonic disturbances by injecting harmonic currents directly into the grid. Composition of harmonics. Any distorted waveform is composed from harmonic components and can be decomposed into a sinusoidal at fundamental frequency and a number of sinusoids at harmonic frequencies. The harmonic current frequencies are n times the fundamental frequency in a 50 Hz network. A 150 Hz, 3 by 50 Hz, waveform is the third harmonic, a 250 Hz, 5 by 50 Hz, waveform is the fifth harmonic and so on. The decomposition of the waveform in the figure would result in the fundamental, which is superpositioned by the 5th, 7th, 11th, and 13th harmonic. Total harmonic distortion, THD. The amount of harmonic distortion is expressed as a THDI percent value, where I1 is the RMS value of the fundamental frequency current and N is the nth harmonic component. Below an example TOFA 6-pulse rectifier harmonic current content. Distortion power factor. The increasing harmonic content on grids requires to acknowledge that power factor has two components. The phase shift of the nominal frequency current causes the displacement power factor. Currents at higher order, harmonics, cause the distortion power factor. Example, a typical VFD with 6-pulse diode bridge can easily cause. Nonlinear loads are typically causing a bad power factor. THD indicators. Which harmonics are critical? Voltage THD. THD V8% reveals an important harmonic pollution. Malfunctioning is probable. THD V5% less than 8% reveals a significant harmonic pollution. Some malfunctioning is possible. THD V less than 5% is considered to be normal. No malfunction need be feared. Current THD. THDI greater than 30% reveals an important harmonic distortion. Malfunctions are probable. The D 10% less than 30% reveals a significant harmonic distortion. Malfunctions are possible. The D less than 10% is considered to be normal. No malfunction need be feared. Inductive and capacitive. Any load not being purely resistive causes a phase shift in current. Resistive current can be lagging or leading over the voltage. The main players known for each effect are inductors and capacitors. Loads like motors or transformers are inductive and cause the current to lag 90 degrees, top picture. Loads like capacitors cause the current to lead 90 degrees over the voltage, bottom picture. Reactive power is needed to enable real work by magnetizing motors or transformers, lagging, or rectifying AC to DC, leading. But it should not be transported through the grid since it consumes capacity of the network. Power factor. Examples. As the power factor goes lower than 1, it means that the load requires more reactive power to operate, hence more current from the supply. To improve the power factor can be done by delivering locally the necessary reactive power so that the value of the current and consequently of the power flowing through the upstream network can be reduced at the same required output power. On the right side of the slide you can find a list of estimated power factor values for the most common load applications. Poor power factor. Oversizing of equipment. Generators and transformers are sized according to the apparent power. At the same active power, the higher the reactive power to be delivered, the higher the apparent power. Thus, by improving the power factor of the installation, these machines can be sized for a lower apparent power, but still deliver the same active power. As an example, figure shows the variation of the transmissible power for MV/LV three-phase transformers as a function of the cos phi of the load. Poor power factor. Oversized cables and increased losses and voltage drop. As explained in the previous example, as the power factor goes down the current goes up, leading to an increase in the size of conductor to avoid overheating the cables. Also, as the current increases, the losses increase according to below listed formulas. Summary. Power factor is a measure of how effectively incoming power is used in your electrical system and is defined as the ratio of real to apparent, total, power. A poor power factor can contribute to equipment instability and failure, as well as significantly higher than necessary energy costs since it means that more current is required to perform the same amount of work. Causes. single-phase and three-phase induction motors, industrial furnaces, harmonic currents, electrical discharge lamps, effects, motor failure and electrical or electronic equipment failure, overheating of transformers, switchboards and cabling, nuisance tripping of circuit breakers or fuses, unstable equipment operation, high energy usage and costs. Solution: UPS. Reactive power compensation methods. Voltage unbalance. In a three-phase system, the degree of voltage unbalance is expressed by the ratio between the RMS values of the negative sequence component and the positive sequence component of the voltage. It could be calculated approximately according to the below equation. Voltage unbalance. Sources. Common causes of voltage unbalance include: faulty operation of power factor correction equipment, unbalanced or unstable utility supply, unbalanced transformer bank supplying a three-phase load that is too large for the bank, unevenly distributed single-phase loads on the same power system, unidentified single-phase to ground faults, an open circuit on the distribution system primary. Here below you can find a list of the most important equations to be used when dealing with UPS. The purpose of these equations is split input, UPS input side, battery side, and load side. UPS main parameters summary.